Hello, my AB children. Today we're going to look at definite integral, section 6-7, and it's going to be a discussion between derivatives and antiderivatives and how they relate to each other. So, an antiderivative of a function, f of x, is the function capital F of x. So you'll see a distinction between the notation that they use, whose derivative is f of x. So what the heck does that mean? For example, let's let f of x be 3x squared, and the derivative of 3x squared is 6x. The expression 3x squared is an antiderivative of 6x, and the question is why. If you take the derivative, d over dx is the notation I'm going to use for that. If I take the derivative of 3x squared, what do I get? And the answer is 6x. So it is the antiderivative for the function. If you take the integral, when we take an integral, it's like taking the antiderivative of a function. So integrals and antiderivatives go together. The area under the curve is represented by an antiderivative, and you're like, what on earth? So if I'm looking at some kind of an integral that goes from a to b, some section of the graph, for some function, right? Then what I'm really looking at is the area under the curve, and I can have any curve I want. I'm going to make mine go like this. Here's a to b, and what I'd really be looking at is the area under that curve between a and b. Well, it's the same thing as finding the antiderivative, same idea as finding this antiderivative for the function, and you're going to see that as we go through the examples and such today. So, how did you get this derivative from 3x squared, right? The power comes down in front, you multiply, and you take one less power, right? That's how we get the power rule for this thing. Well, there's a power rule for antiderivatives, and the power rule says this. Oh, actually, this is the rule for derivatives. So just like I was talking about, the n would come down in front, and then you would take x to one less power, n minus 1 power. So our rules were multiply by the old exponent and then subtract 1 from the exponent. This is going the other way. Now I want to figure out what it would be if I went and added a power on. So it's going to be x to the n plus 1 power over n plus 1. So this time, to get the antiderivative to go in reverse, if I were to go in reverse, I'd be adding a power on. If I want to undo this and go in reverse, I'd be adding a power on and then dividing by the power. So step 1 is add 1, and this is really important. This is going to be used a lot in the next few sections. Add 1 to the exponent. Okay, add 1 to the exponent, and then divide by the new exponent. And what you're doing when you do that is finding the antiderivative, finding capital F of x. So you can find derivatives down a power, and now you're going to be able to find antiderivatives going up a power. So instead of multiplying by the power, you're dividing by the power. They kind of inverse each other. Okay, so let's try some examples. First one they have here is a nice easy one. Given the function f of x, you've got x squared. Find the antiderivative, find capital F of x. So let's apply this rule. We're going to use this rule right here. So if I do that, capital F of x is going to equal, well, add 1 to the power. 2 plus 1 is 3. Divide by the power. But here's the situation with these. There's a rule that you have to apply, and I'm going to put in the margin a little bubble so that we kind of remember it. When you find an antiderivative, you need to add c. Now just write for now, and then I'll explain why. Add c when there are no bounds. All right, so this is important, important, important. So I'm going to bubble this in. So here's the story. If I go over here, there's no bounds. They haven't given me boundaries on this thing. So I have to put a plus c at the end for me to have the correct antiderivative. And you're like, what the heck is c? C is some constant. It could be any number at all. It could be positive. It could be negative. But it's some kind of a constant. And here's why. You're going to check it. We're not going to check these all the time. But this time we'll check our answer. If I want to go backwards from my antiderivative, if you go backwards and find the derivative of this, you should end up with the original function. So let's see if that works. If I apply the derivative rule, this is the same thing as 1/3 x cubed, right? Is the same thing, plus c. So if I find the derivative of that, the 3 comes down in front and I take x to 1 less power. So I end up with an x squared. And what's the derivative of a constant? 0, right? So there always could be, when I find these antiderivatives, there always could be some kind of constant added or subtracted to the function. And all that does graphically is switches it vertically. So it could be higher on the graph or lower on the graph, but it still has the same shape and characteristics. So the function is going to have the same characteristics, but this c could shift it vertically up or down. And the derivative of a constant is 0, so it doesn't affect what the original function was. The original function then was just an x squared. So anytime you find antiderivatives, add a c at the end because there's no bounds involved. And we're going to see examples in a few minutes that have bounds, and so you'll see the difference in what they look like. All right, so let's find antiderivatives. Here we go. We're just using the power rule totally. Well, this one's a little bit messy. I think maybe before I go to capital F, I'm going to keep it at f of x so that I can prepare it to be derivatived. So the first term's a 5x cubed. The next one I'm going to put as plus 6x to the negative 3 and then minus 1. I'm preparing it just so I can find this integral, this antiderivative. Now I'm ready to capital F of x this. So I add a power on, divide by the power. 5x to the 4th over 4 plus. Add a power on. Now this is negative 3. Negative 3 plus 1 puts me at negative 2. So 6x to the negative 2 over that power, negative 2. This one's kind of goofy. This one, if I add a power on, there is no x. Well, technically there's an x here that's x to the 0 power, right? X to the 0 power is 1. And so if I add a power on, so it's going to be minus, add a power on, it's going to be x to the 1st plus c. All right, let's pretty it up. That's the last piece, is to see if you can simplify any of these fractions. 5 over 4 doesn't change, but 6 over negative 2, that can change. So we've got a couple options for this. F of x equals 5x to the 4th over 4 minus 3x to the negative 2 minus x plus c. You could put this as 3 over x squared. I think that's what they did in their video. Same thing. Doesn't really matter much. All right, going to do the same thing with number 3, except I want to pretty it up to be able to antiderivative it. So I'm going to make the square root as a power of 1/2 and make the other square root a power of negative 1/2. All right, if I were to apply the rule, now you got to watch it with your fractions, capital F of x, add a power on, 1/2 plus 1, 1/2 plus 2 over 2 is 3/2, x to the 3/2, divided by that power, 3/2, plus, add a power on, x to, this is a 3 in front, x to the 1/2, negative 1/2 plus 1/2, plus 1 gives you a positive 1/2. So now it's x to the 1/2 power over 1/2 plus c. Now when this thing comes together, interestingly enough, you end up dividing by a fraction. Now think about that from back in the day of our elementary math kind of classes, that if I were to divide by a power, it's really multiplying by the reciprocal. And so what happens with these things, when I divide by 3/2, it actually flips, it reciprocals on us. And divided by 3/2 would be like multiplying by 2/3. So my first term is really 2/3 x to the 3/2. This 1/2 dividing by 1/2 is like multiplying by its reciprocal 2. 2 times 3 is 6. So my second term is a 6x to the 1/2 power and then a plus c. So when you're dividing by these, remember it's like multiplying by the reciprocal. That's how you're coming up with the values that are now the coefficients in front. So I'll put a little note here. Multiply by reciprocal. Can I fit it in? Kind of. You got the idea. And then they're reminding you about the trig functions and how they work with their integrals. I mean, this is just rules that you have already that you know. We know that the integral of sine would be like what the answer is after you derivative. So that means it has to be negative cosine of x. Because if I take the derivative of negative cosine of x, I get the sine of x. And this guy is going to be the cosine of x. And so its integral, antiderivative, is the sine of x plus c, because the derivative of sine is cosine. Okay? They're just reminding us because that's going to come up in a bunch of problems, of course. All right, flippy-doo. Here is the fundamental theorem of calculus, part 1, which we didn't talk about. We talked about the fundamental theorem of calculus, part 2, but this one is now part 1. If f is a continuous function on the interval from a to b, then the area under the curve from a to b is represented by the integral. That's kind of what I showed you on the front page, right here. The area is represented by this integral. If I want to figure out this area, got to take the integral from a to b. So they're just kind of emphasizing that a little bit here. But here's the story. If I want to actually evaluate this, what I need to do is find the antiderivative, capital F of x, and then plug in whatever the upper bound is and subtract away the lower bound plugged in. Now, this capital F is talking about you got to find the antiderivative. So before you can actually plug numbers in and evaluate it, you've got to figure out what the antiderivative is. And so you'll see in the next few examples that these are a little bit different than the ones we did on the front page. If I look, these now have bounds involved. And since they've got bounds involved, you're not going to have to put that C value. These are actually going to come out to be answers that are numbers. These are going to be some type of numerical answer. They say use a calculator to check your answer. I'll show you one of them with the check, and then that way you can know how to do it. But we're not going to check all of these. So here's what I've got to do. Job number 1 is figure out what capital F of x is. By the way, write small because these guys get pretty involved. Capital F of x. I have a 4 minus 6x, and I'm going to apply that power rule. So 4, there's an invisible x, so it's x to the 0. If I add a power on, it's going to be x to the first, and so this first term is a 4x. Next one, 6x. So I have 6x, add a power on, that's a square. All right, so minus 6x squared, divide by the power. And so I'm actually going to be plugging numbers into this. So what I want to do is make it as simplified as I can. This guy's a 4x minus a 3x squared. And so as I look at this, now here's what I have to do next. There's a couple different notations that they use for this, but if I have my capital F of x, once I've found my antiderivative, I say 4x minus 3x squared. You might see it written this way with just one vertical line after it and your bounds below. Sometimes it'll be bracketed in, and I'll use a little variety as we do it, just like we kind of use varieties when we're naming derivatives. Do we use y prime? Do we do f prime of x? How do we want to write it notation-wise? But I'll show you the first one this way. And what that really means is that you want to find f, capital F, of 5 minus capital F of negative 2, fundamental theorem of calculus. So we found the antiderivative, that's step 1. Step 2 is plug those in. All right, well, if I put a 5 into this, then I'm going to use lots of different brackets and parentheses and things. I'll have 4 times 5 minus 3 times 5 squared. Right, wouldn't that be what I get if I plug a 5 into these two locations? That's what it would look like. Then I'm going to subtract. All right, second one's going to be, put a negative 2 in. So 4 times negative 2, I'm trying to squeeze this in the box, it's probably not going to work, but a girl can try, minus 3 times negative 2 squared. And then simplify it out, do your algebra. This is where the most mistakes take place. You know, it's not the calculus that messes kids up, it's all the algebra stuff. So just be careful. You have 20, 4 times 5, 25 times 3 is 75. So your first set of brackets there gives you this. Second set of brackets, minus 4 times negative 2 is a negative 8. Negative 2 squared is 4. 4 times negative 3 is negative 12. And you're going to keep going down until you get your answers. So 20 minus 75 is a negative 55. Negative 8, negative 12 give you negative 20, but it's a minus a negative 20, so we're going to make that plus 20. And then add them up, and you get an answer, and your answer is negative 35. Well, that would be the same thing that you would get if you were to look at if you were to graph this and then figure out what the area was between those two locations. It's the same thing as finding that area. But you're actually doing it via algebra, doing it through the calculus stuff. So using antiderivatives. That's it. All right, next one. I've got a square root of x minus 1 over x squared. I'm going to be applying the power rule to this, but obviously I don't like the form it's in right now. So this, I'm just going to go up above just for the safe place. I don't think there's a lot of room in the box. So here it is. This would be x to the 1/2, my square root, right? Minus x to the negative 2. That's what I want to apply the rules to, this the antiderivative rule. So add a power on, divide by the power. We're working on finding our capital F of x. You can't do the plug-in until you get the capital F of x, the antiderivative. Okay, so add a power on. That's going to be x. I'm going to leave a little space. X to the 1/2 plus 1 is 3/2. Divide by the power. If I divide by 3/2, we saw this on the front side. If I divide by 3/2, I have to multiply by the reciprocal, so that's 2/3. So the coefficient here is going to be 2/3. All right, then I have minus. Add a power on, x to the negative 2 plus 1 is negative 1. X to the negative 1. Divide by the power. Divided by a negative 1 would just be a 1 on the bottom, but it changes this because it's a negative negative now. And so as I look at my capital F of x, my antiderivative, as I go to plug numbers in, I'm going to put it this way again. I'm going to have 2/3 x to the 3/2. And this one I'm going to put written the other way as 1 over x. All right, and I'm going to use, this time I'm just using a bracket on the other end. And I've got my 1 and 4. And so then it's a matter of just plugging it in. So if I put a 4 in here, I'll have 2/3 times 4 to the 3/2 plus 1/4, right? That's going to be my front end. And my back end, f of b, f of a is going to be 2/3 1 to the 3/2 power. You can see I'm trying to just keep it inside the box. It's not happening. No go. Plus 1/1. All right, let's work on simplifying this guy. Kind of nice. The denominator, if you remember with exponents, the denominator tells you what root you're taking, and this tells you what power you're raising it to. So I have the 2/3 in the front. I'm going to keep that there so we don't get too confused. This 4 to the 3/2 power, so I take the square root of 4 is 2. 2 cubed is 8. And then plus 1/4 minus. 1 to any power is 1, so this is just 2/3 plus 1. All right. 2/3 times 8, I have to multiply before I can add and subtract these things. Remember your Aunt Sally? So 16/3. I have 16/3 plus 1/4. And then I have 2/3 minus 2/3 minus 1. Distribute the negative. Common denominators across the board there would be 12s. 3 times 4 is 12. And so this changes into, if I get them into common denominators of 12, this would become 64 times 4. So 64/12. Plus, if I change this as times 3, 3/12. If I change this as times 4, 8/12. And 1 is 12/12. Add them up, subtract them, do your deal. 47/12. That's your final answer for that guy. Believe it or not, the trig one that comes next is not as much work as some of the others. You just need to remember your unit circle. So I don't know how that's going to fly with you, but let's see. I have a 4. The 4 is a constant in front. And if you remember from the section we did on the properties of integrals, you're allowed to pull that out. So just keep the 4 outside. Here's my actual integral. That's the same thing. I can pull constants out. That's good. And then if you think of the bottom of the first page, the integral of sine. So I'm looking at the bottom of the first page. This guy, integral of sine is negative cosine. Now plus c, we don't need c's when there's bounds. These problems have bounds and therefore we are not seeing. In fact, we probably should put that in a bubble out to the side here. No c because there are bounds. You are specific with this one. When they give you the bounds, they're telling you that you're looking at just a certain portion of the graph and you don't care about what's going on in another location. Where the other one's more of a general formula for the integral, which is why you need the plus c. All right, anyway. So I have 4 times in my problem. We said that the integral of sine was negative cosine of x. And you would have to deal, if this had a number next to it with the angle, if it were 2x, you'd have to deal with that, and I'll show you that in some problems when they come up. We're not there yet. So what I'm really looking at is negative 4 cosine of x. That is my antiderivative, and I want to evaluate it going between 0 and pi over 2. So there's a few ways that you could write this algebraically, but since we took that 4 out, since I took the 4 out, it's going to be negative 4, and then I guess I could even bracket it this way. and then do cosine of pi over 2 minus the cosine of 0. That's one option. There's a couple different ways you could write this, but here I go. That negative 4 gets attached to both of them, so you could either negative 4 times this minus negative 4 times this, or to keep the negative 4 out there in the brackets and work your way through. So cosine of pi over 2, go up pi over 2 is 90 degrees. So if I think of the coordinate there, that's 0, 1. Cosine is the x coordinate, so this would be 0. So I've got negative 4 times 0. Cosine of 0, go to the unit circle, that's the very beginning, that's the coordinate 1, 0. So it's going to be a value of 1, the x coordinate, so 0 minus 1. And if I take and multiply them out, negative 4 times negative 1, I end up with an answer of 4. All right, here comes the last one. Well, I think is it the last one? Yeah, it is. Last example anyway. Number 7. So if I look at number 7, this is a classic AP kind of question too. If the derivative is x squared minus 2 and you have, oh gosh, my dog just scared me. Did he scare you? That's a Levi. Anyway, if the derivative is x squared minus 2 and you have an original function coordinate of 1, negative 2, what's the coordinate value at 3, when x equals 3? So what they're saying to you is on the original function, you have a coordinate at 1, negative 2. They want to know if you're at x equals 3, what's the y coordinate? And you're like, how am I supposed to figure that out? I don't know, right? Well, here's what you're going to do. You're going to, if you want to go backwards, right, you have the derivative and you want to go backwards and figure out what the function was, all you need to do is take the integral. But you know what it is at 1. You know at 1 it's negative 2. So here's how this one starts out. I'm going to show you and then I can explain it maybe better. You know what it's doing at 1. At 1 you're at negative 2. You have no idea what it's doing anywhere else, but you know at 1 it's at negative 2. You're trying to figure out what it is doing at 3. So you're traveling, you're at 1 and you want to go to 3. And again, you don't care what it's doing at 10 or other locations. You only want to know what it's doing at 3. So you're going to set up an integral. You know you're looking for what it's doing from 1 to 3. And so we know that this derivative is x squared minus 2, and I want to go backwards and figure out what the actual function would be. All right, so if I do that, let's antiderivative. The negative 2 just stays chillaxing in the front for a while until we can combine it with something else. If I antiderivative this, I add a power on, divide by the power. X cubed over 3. This has an x to the 0 with it, so that means it's going to be 2 times x to the first. And what you're going to do is you're going to evaluate that from 1 to 3 like we did with the other ones, f of b minus f of a it. All right, so here's where we go. Get negative 2 that's working in front, just staying there. If I plug a 3 into this, 3 is going to be 27 over 3. 3 cubed is 27 over 3. We'll come back and simplify that in a minute. 2 times 3 is 6. Maybe I need double brackets here. Minus f of a. Put a 1 in there. 1 cubed is 1, so 1/3. 2 times 1 is 2. And then it's just a matter of cleaning it up, right? 27 over 3 is like 9. 9 minus 6 is 3. So I've got negative 2 still out front. Plugging away. This gives me 9 minus 6 is 3, we said. This one you have to be a little careful about the distributing the subtraction sign. So it's negative 1/3, so it's going to be minus 1/3, but it's going to be plus 2, right? Negative, negative 2. Well, that ends up knocking out. Now think about how you're just adding terms now. Now you're ready to deal with Mr. Negative 2 that's been relaxing out front. Guess where he goes? He goes bye-bye, because the negative 2 and the positive 2 cancel each other out. So what you're left with is just 3 minus 1/3, or 2 and 2/3 as a final answer for what that would be. So your y coordinate would be 2 and 2/3. All right, that takes care of the examples. We're going to do a few practice problems together and then call it a day. Number 2 was the first one that I chose, and of course I chose the trig function guy, right? This one says, find the value. Oh, I never showed you on the calculator how to check your answer. I show you with this one. All right, so sine of x minus x is my function. I have to first, they want me to find the value of the definite integral. So in other words, this one has bounds. I don't need the plus c, but I do need to go backwards and find capital F of x, antiderivative. We said that the antiderivative of sine was a negative cosine, and that the antiderivative of an x, add a power on, divide by the power, so it would be an x squared over 2. And what I'm going to do is evaluate that from 0 to pi over 2. All right, so here I go. Plug it in. I have my first grouping is going to be a negative cosine of pi over 2, upper bound, minus pi over 2, well, pi squared over 2, right? And then I'm going to have minus the 0. So negative cosine of 0 minus 0 squared over 2. If I go cosine of pi over 2, again, I'm up at the top of the circle, so that's 0, 1. My x value is 0, so this becomes 0. Minus pi squared over 2, whatever that is. Plus negative, negative. Cosine of 0, go to 0, and my coordinate is 1, 0, so it's a 1. And 0 squared over 2 is just going to be a 0. However you want to write that 0 in there. Okay, so I end up with an answer that is, oh, did I forget something? Let's see. Pi over 2, I'm looking at this should be written, this should be a little bit different. Let's see, x squared, pi over 2. Did you catch this in here? Ugh. Let me go back and see if I can fix it and not confuse you. If I put a pi over 2 in here, it's going to look like this. Pi over 2 squared divided by 2. Did y'all see that? Did you catch that in when I was trying to do it? All right, so what that really is, I'm going to go over to the box over here because it's really pi over 4, pi squared over 4, divided by 2. Right? Pi squared, 2 squared is 4, pi squared over 4 divided by 2. So that's going to be pi squared over 4 times 1/2. Gives me, this term is really pi squared over 8. Ooh, my, that's a bit different. So when I put this together, my answer 0 minus pi squared over 8 plus 1 is the same thing as 1 minus pi squared over 8. Now I said I'd show you on the calculator how this thing works, which I will. Give me the crap calculator here. It's going to be easiest to show you if we decimal out this answer. So if I have 1 minus, let me do the pi squared over 8 first. So if I do pi squared, hopefully put it where you can see it. Pi is the caret button, so second caret, pi squared divided by 8 gives me 1.2337, and if I do 1 let's see, pi squared over 8, yep. 1 minus 1.2337. I get negative 0.2337. So negative 0.2337. Alrighty. So what I want to do is show you how to find the integral. I think I might have shown you this in one of the previous videos too, but that's okay. Go to your y equals, and I'm going to put this in my y3 because I'm using the other two for something else in a minute. If I put in the function sine of x minus x, so sine of x minus x. All right. And then I graph it. Quite the graph, right? There it is. And so then I'm going to go to my F5, my math menu, down to number 7. They want to know what's the lower limit, and so my lower limit is 0. And my upper limit is pi divided by 2, so pi divided by 2. And there you go. You got the same answer that we got doing it algebraically. So negative 0.2337. So that's how you're checking yourself if you want to check yourself on these answers. All right, next one that I wanted to do is number 8, which is a calculator question. They didn't show you examples of this type of one using the calculator to do this. However, the procedure is the same. Use the given information to find the value of the function. They give you f of 1. They want to know what is it at f of 4. It'd be nice if you could see me. All right, there it is. So this is like the last question of the examples that we just did. So you know where you're at 1. You know the value is 0.751. And you're trying to get to 4. So you're going to add on the integral. You're at 1. You want to get to 4 for this derivative here. So you've got the derivative goes inside the integral. It's the sine of 3x plus e to the x. Derivatives, our integrals always want that with respect to x at the end. And so you're going to have 0.751 plus, and then you're going to your calculator, and we're going to do the same exact type of thing we just did. I want to put in my y1, and there it is. I have this one typed in already. So I'm going to graph it. Maybe. Oh, he does some fun stuff for a sine graph. He's like moving along, and then he's like, oh, wait a minute, I still have the other one checked. Yeah, I don't want that guy. There it is. Now this one, I'm hoping it's going to be happy. Sometimes when it goes off the screen like that, it won't evaluate it. So let's just see what it does. If I do F5, 7, lower limit is 1, upper limit is 4. There it is. So I get an answer that is 51.2686. 51.2686. And so if I add that with the 0.751 where I started, that gives me a value of 52.0195. All right, so that's how you're using your calculator to do those problems. All right, just a couple more, I promise. Number 12 is the next one that I wanted to look at. It's very, very, very similar, except the wording is just slightly different, and so I don't want it to throw you off, but capital F of 2 is negative 0.13. What's capital F of 5? And the antiderivative is ln of x over x. This is done the same exact way. They're all the antiderivatives. They're all, this is an antiderivative, this guy capital F, so you can use the same methodology to be able to figure this out. So negative 0.13 plus the integral from, we know what it is at 2, We want to know what it is at 5. And so there it is. And I put my ln of x over x right in there. And so again, I'm going to go to my calculator and figure out what the ln of x over x is. I can put it in y3. We've got ln of x divided by x. All right, let me uncheck number 1. By the way, it's just F4 to check it or uncheck it. And so I'm looking at this guy, and I should be able to graph it now. Ln of x over x. All right, and I want to know what it is from 2 to 5. So F5, 7, lower limit 2, upper limit 5. And I get 1.055, I'm going to say, around it. So negative 0.13 plus 1.055, that gives me a value of 0.9249-ish. Okay, so don't let the verbiage there change. It doesn't change the process of what you're doing. All right, next one is, and again, this is a graphing thing we're going to do, number 14. 14 is next. This is the last one. 14 says, let f of x be the integral from 0 to x squared of cosine of t dt. At how many points in the closed interval from negative square root of pi to positive square root of pi does the instantaneous rate of change of f equal the average rate of change of f on that interval? Well, the instantaneous rate of change is the derivative, right? So if I'm looking at this, if I'm finding the derivative, f prime of x, remember how this works. We saw this in a previous unit. It's going to be the cosine of x squared times the derivative of that power. And that's what the rule is. It's the fundamental theorem of calculus. If this bottom is a constant of any sort, then this is how you're working with it. So times 2x. Well, if that is, let me make it prettier, I guess. If I'm looking at what that would be what my instantaneous rate of change would be for this guy, looking at it. If I look at the original function, that would be the derivative of what this is. So what's the, I guess I should go the other way. What's the antiderivative? What's the integral of cosine? And the integral of cosine is sine. This would be looking for what the actual function is. The function is the sine, in this case of t, going from 0 to x squared. Actually, I don't even know that I need to go through all this. I'm looking at my answer and looking at, I think we're good to, anyway, this would then become my function being, I guess this would be a way to check it. The sine of x squared, remember f of b minus f of a? So this would look like the sine of x squared minus the sine of 0. And the sine of 0, if I go to 0, that's 1, 0, so this would be 0. So this would just be the sine of x squared. Or sine of x squared, not sine squared x. Sine of x squared. So that takes care of the instantaneous rate of change. And all this work in here I think you really didn't have to do. But that's all right. It's good to talk about. Now I'm going for the average rate of change. Well, average rate of change is like the slope. So my average rate of change is like finding the slope. So how would you find the slope of this guy? Well, I guess we did need to find it for being able to do this next part. So my function was sine of x squared. I want to know what f of, which again, this is my f function, negative square root of x, or pi, in my case pi, right? Other way around, positive. Let's do the positive first, f of b minus f of a. So positive square root of x minus f of the negative square root of pi over pi minus square root of pi minus a negative Square root of pi. What's with these square roots and pi's together? I don't know. All right, so let's plug it in. We know our function is the sine of x squared, thank God, right? So I can square these square roots and get rid of them. So this one would be the same thing. If I put a positive square root of pi in here, it's going to be sine of pi. The square root and the square are going to cancel each other out. Same thing's going to go when I do this. It's going to be, though, the sine of a negative pi. Over pi, I guess it's going to be, if I take these two things, it'd be like adding them. So I would have 2 square roots of pi. Well, let's evaluate. We can evaluate that out and get a number. Sine of pi, if you go over to pi, pi is at -1, 0. Sine is the y value, so that would be 0. If I go to negative pi, it's exactly the same coordinate, isn't it? It's just going the other way, the other direction to get there. That's also going to be 0. So I end up with 0 over 2 square roots of pi, which is 0. So the question is, back to the question. What was the question? I don't know. We've been on a math journey trying to get there. When does the instantaneous rate of change, derivative, equal the average rate of change? So it comes down to this. It comes down to the cosine of x squared times 2x, you can put it in the front or in the back, whatever, equals 0. You want to know how many times in this interval, at how many points in this interval does this happen? So you go to your handy dandy calculator. Thank God it's a calculator question. And in my y equals, I am going to put 2x, and a lot of times this calculator likes you to have a times symbol. See how I have a times in there? It automatically put it, I normally put it in as 2x times and then the cosine of x squared. So you're putting that in your calculator and you want to graph this thing. The graph is kind of funky. Look at this oscillating deal. He goes crazy and then he kind of mellows out and then he goes crazy again. It's like, all right, here I go. I'm taking a breath. Everything's all right. And then it goes whack job again. And the question is, between negative square root of pi and positive square root of pi, how many times does it cross? How many times does it equal 0? How many times does it cross the x-axis? This would be impossible for you to see. Way too much stuff going down. So you're going to go to the window. Oops, I didn't mean to do that. Hold on. I want to go to the window. So that is, there we go. I want a negative, I did it this way. I put pi in, I don't know if you, there you can see me better now. I put pi in and I raised it to the 1/2 power, 0.5. That's the same thing as the square root of that negative pi. And I put positive for my other x max. I did the positive of that. It's probably just the same value, that 1.77, yada yada. Pi to the 1/2. Okay. And then I graphed it again, so that my window only shows that those values between that negative square root of pi and the positive square root of pi. And the question is, how many times does it equal 0? And we say 3. You got 3 locations where it crosses the x-axis. 1, 2, 3. There it is. So your answer should be D. How about that? Now on this page, important, you are not doing number 16. Take him off the list. Okay? All right, that's it for this section, and I will meet you again to talk about, I believe indefinite integrals is the next one, section 6-8. So 6-7 is done, and shoot me an email if you have questions.